Between 2021 and 2024, financial markets treated artificial intelligence as a weightless, frictionless software revolution. The prevailing mindset, AI was detached from the physical world. Peak market valuations were driven by a single assumption that AI output could scale linearly alongside consumer demand. If code can be copied infinitely, the logic suggested that AI growth was unbounded. In 2025 and 2026, that logic failed. A massive market correction wiped out over $1 trillion in tech valuation in months. Rather than a decline in software demand, this correction was caused by the industry slamming into a hard ceiling of physical infrastructure and natural resources. AI functions as a heavy, highly constrained physical asset. It is strictly bound by the finite resources of the planet. To understand the first physical choke point, look at the global semiconductor supply chain, which currently centers on a single industrial hub in Taiwan. Manufacturing an AI processor requires a two-stage process. First, you print the silicon wafer, then you perform a complex assembly step called CoWoS, or chip-on-wafer-on-substrate. Global AI capacity is now strictly capped because TSMC's packaging lines and SK hynix high-bandwidth memory production are fully booked through 2027. The industrial footprint required to make these components is immense, and it cannot be scaled overnight. The U.S. government attempted to break this bottleneck with the $52 billion CHIPS Act, designed to reshore this entire manufacturing ecosystem back to American soil. Despite that massive infusion of capital, new fabs in Arizona and Ohio have faced massive delays and cost overruns. Building these plants outside of Asia has proven slower and more expensive than expected, pushing back the timeline for domestic supply to 2028. Advanced algorithms have little utility without access to the geographically concentrated and fragile physical ecosystem required to build them. Once built, the chips must be housed in warehouse-scale data centers. These facilities are now placing an unprecedented strain on the national power grid. For 20 years, U.S. electricity demand was flat. Now we're bracing for a 15 to 20% spike over the next decade. AI requires firm power, a steady 24-hour flow. Fluctuating renewables like solar and wind cannot guarantee this massive baseline requirement. This need for firm power has triggered a scramble for alternative baseloads. Tech corporations are now funding the reactivation of retired nuclear plants and investing in next-generation geothermal energy to secure their own power supplies. The speed of the AI revolution is now hard-capped by the regulatory and construction cycles of the power grid, which move in decades, not months. Locally, the problem is thermal engineering. Thousands of servers running at full capacity generate enough heat to destroy the hardware, if not cooled constantly. This creates an engineering trilemma, a strict trade-off between compute performance, electricity, and water. Operators rely on evaporative cooling, using massive amounts of local water. Switching to closed-loop systems saves water, but causes the required electricity to spike into the red. Evaporative cooling systems consume up to 80% of the water they withdraw, sending it into the atmosphere instead of returning it to the local river or aquifer. This creates a secondary crisis of water quality. The water that is discharged is often filled with chemical treatments and heat, straining local municipal plants that were never designed to handle industrial wastewater at this scale. Environmental constraints and local resistance from rural communities protecting their drinking water form the ultimate, non-negotiable limit on data center expansion. Taking a macroscopic view, we can see the tech industry shifting toward a heavy industry model, funding its own energy infrastructure to bypass the limitations of the public grid. Hyperscalers are now vertically integrating, designing their own custom silicon to mitigate the price hikes and capacity limits of the global foundry market. They are acting as resource managers, directly deploying grid-scale clean energy and liquid cooling technologies to bypass the physical walls that stalled the initial AI boom. Success in this new era belongs to those who master heavy engineering, supply chain logistics, and resource management. Smarter code is no longer enough to win the race.